Morning, everybody, and thank you for coming to the course. So this course is based on this book, and I think most of you have a copy. And we wrote this book a couple of years ago, and what we aimed to do was really to give you a practical guide. So this word practical guide is very important. And this is a book which was mostly written by the students. And the students are the people in the lab who are really doing the experiments and know all the pitfalls. So it's not really to say, oh, this is a wonderful technique, it can do all of this, but really to tell you the do's and don'ts of these techniques. So I hope you find it useful. And today we're going to not be able to cover everything. So I'm going to give a brief introduction and talk a little bit about sample preparation, calorimetry, and chemical shrinkage. Then I'm going to talk about X-ray diffraction, then electron microscopy. TG Vanderley is going to talk about this afternoon, and then I'm going to finish by talking about techniques for looking at pore structure, proton NMR, and MIP. And if any of you want to follow up on this course, next month we're bringing out this MOOC, that's massively online open courses. This starts on the 18th of September, and this course is called Cement Chemistry and Sustainable Cementitious Materials. It's got a lot about materials characterization, and you can go and watch these lectures. It's absolutely free. If you follow the whole course and you want a certificate, then I think you have to pay 50 francs or something like that. But if you just want to watch the lectures, this is absolutely free. And not only do we have lectures, we have practical demonstrations in the lab, how to prepare your samples and everything like that. So I think you can really find that useful. And this is written very small down here. I know you won't be able to find it, but I think if you just Google this cement chemistry and sustainable materials, you will get onto it no problem. And lastly, for those of you who want to follow up, every year we run a doctoral school which is mainly oriented to talking about materials characterization. This runs in April, and if you're interested in that, I can give you more details. So we're going to start with an overview of what we're trying to do when we make materials characterization of cementitious materials. And generally the idea is this. We have the hydration reaction, during which the anhydrous materials react with water to give us hydrates. So if we imagine how things are changing over time, we start here, the unreacted cement is reacting, and it's been replaced by, in this simple case, if we were just thinking about the C3S reaction, by CSH and by calcium hydroxide. You'll note that the overall volume is going down because the total volume of water and anhydrous is slightly larger than the volume of the hydrates. And if we want to make this more complicated for a real cement where we have many different phases, not only C3S, but C2S, etc., and then lots of other hydrate phases, then it's a little bit more complicated. But this is generally the idea of what we want to do. And we have a couple of techniques which I'm going to talk about here, which can really follow the reaction overall. And then different techniques which can give us much more details on exactly what phases we have and how much of them. But these techniques we usually have to make discretely. That's to say we have to make a paste, we stop it at, say, 10 hours, we measure it, we make another paste, we stop it at 1 day and measure it, and so on. And this is what I mean by continuous and discrete methods. So where are we? So this is what we want to determine: the phase content, the distribution, and also the kinetics. And this can then impact we can also use these same techniques to study durability. I'm not going to talk much about that today because there isn't time. But we can also use the same techniques to look in terms of durability, how the microstructure is affected by the environment, and what are the mechanisms responsible for degradation. So the characterization methods we're going to talk about, we have these two continuous methods, calorimetry and chemical shrinkage. Then for the solid phases, the main methods which we're going to talk about today are X-ray diffraction, thermal analysis, and scanning electron microscopy. And for looking at the pore structure, we have this proton NMR relaxation and mercury intrusion porosymmetry. So before we go into more detail, I just want to underline some basics which are very important. Now, the first important thing is every measurement technique has an error. There is no single technique in the world which is absolutely precise. You know, even in quantum physics, they have the uncertainty principle. We're not anywhere near at that level of precision. But the point is, don't assume that a measurement is exactly accurate. I have continual problems with students who see small differences and try to overinterpret them. Now, you have also a problem that the smaller the quantity you're trying to measure, the higher the relative error. So if you're trying to measure something that's present in quantities about 50%, you can generally get down to fairly low errors of about 1 or 2% absolute. But that 1 or 2% absolute, if you're trying to detect something that's only present in amounts of 1 or 2%, is nearly a 50% relative error. The second point is about whether you want to study pastes or concrete. So, of course, concrete is the material we use in the real world. But the changes, everything that's changing is generally happening in the cement paste. And this is what we want to study. And therefore, if we look at concretes where we have probably 60 to 70% aggregates, this is going to dilute our signal. So it's the signal coming from concrete, from the paste part, is going to be 1/4, 1/3 of what you have in a pure paste. And if you put that together with the comment above about error, you can see that then your relative errors about detection are increasing. And so for that reason, we generally make studies on paste. But we have to be aware that aggregates do affect the microstructure to some extent. We'll mention a little bit about that in the chapter on microscopy. And of course, you can have some situations where you don't really have an option because you have samples from the field. And this is really one of the major advantages of microscopy methods, that you can focus on the paste regions. And the final comment is, it's never a good idea to depend on just one technique. You really want to try and use several methods in combination and make sure that they tell a coherent story. So looking at continuous methods, the simplest and probably the most well-known is this method of isothermal calorimetry. And this is, the idea here is we measure the heat output. So as the hydration reaction proceeds, it generates heat, and in this instrument, which is called an isothermal calorimeter, we measure that heat release. It's called an isothermal calorimeter because it works at constant temperature, and the heat is the heat that's needed to take out of the sample or put into the sample to keep it at that constant temperature. And you can see the general pattern of hydration reactions we have for Portland cement, that we have initially a very high heat output, but this decreases very quickly. And then after a certain time, the heat release takes off again. We may get various little bumps and everything. We'll talk a little bit about those in a minute. Now, in an isothermal calorimeter, normally you're mixing your paste, you're putting it in the calorimeter, and you're not adding extra water. So this means it's equivalent to a sealed sample. And we can see here by this experiment we did, where we either did a kind of sealed condition, where we didn't have any extra water, or what we could say was a saturated condition where we added a little bit of water carefully on top, that if you're at water cement ratio 0.4 or above, it doesn't really make too much difference. You can see the hydration kinetics here are just about the same in the 0.4 case. But when we go down to lower water cement ratios, in this example 0.3, you can see even from about 1 day, you get a significant deviation between the two samples. In this case here, there's not enough water available and the hydration is significantly slowed down. And of course, the heat of reaction is not telling you what reactions are going on. It's just the sum of everything. Now, through parallel studies with microscopy, etc., we know that if you take a typical heat evolution curve like this, you have mainly in this early stage the A-light reaction, and then superimposed on that you have the reactions of the illuminate phase. So this little hump here will actually be a secondary formation of ettringite, and this one here will be formation of AFM phase. And if you want to know more about the basic chemical reactions and kinetics, please go also to see the MOOC, because all of these are covered in much more detail in that course. So the second method we use is based on this phenomenon of chemical shrinkage. If we write the volumetric equations for the reaction of C3S, this is the 1 volume of C3S, reacts with 1.32 volumes of water, and this produces 1.7 volumes of CSH and 0.59 volumes of calcium hydroxide. So what's important here is you can see that the amount of solid increases dramatically on hydration. So we have 1 solid volume here, and at the end we have just over 2 solid volumes. So this is why the cement works in the first place, because you have this increase in solid volume which joins the cement grains together and gives you this strength and hardening. But then if we look at the overall amounts on each side, we can see that this volume here is slightly less than that volume here. Generally, the amount of overall shrinkage, in this case, we can calculate it as being 7%, but we can say it's in the range of about 7 to 10%, depending on the different phases. And we can use a very, very simple technique to tracking this volume change to measure hydration in a very similar way. So this is the setup, and it's really nice because you can make this setup very, very cheaply. Basically, the only equipment that costs anything substantial is a water bath, and you can generally buy a water bath even for about €1,000. And then in one water bath, you see with this kind of assembly like this, you can have several different measurements, and you can measure automatically with a webcam. In the past, and it's also described in the book, somebody had to come and measure the height of all these drops very regularly, but that's rather annoying, and it's much more convenient to have it recorded in a webcam. So the idea is we have the paste here. This is rather a thick layer, and as I'll explain in a minute, we wouldn't want to have a layer that thick. And then we gently put water on the surface. You don't have to wait for setting, because even after a couple of minutes, the paste has enough cohesion that you can gently put water on top without that water mixing in. And then you have this capillary, so the whole system is sealed. There's water continuously up to here, and then as the volume is decreasing due to the hydration, this water is sucked into the sample and the height of this orange drop is going down. And you can then use that to continually follow the hydration. Now, of course, what's very important is the thickness of the sample. If here we have quite a low water cement ratio, so this is an extreme case. But this shows you that if you have a very low water cement ratio of 0.3, then again, even after about 1 day, you're seeing that depending on how thick your sample is, the water is getting in or not getting in. So only really for this very thin sample here are you really probably following truly the hydration. Now, this is, I say, an extreme case of 0.3. If you're looking at a more normal case of a cement paste at 0.4, then you can use quite typically a thickness of about 5 millimeters is no problem for following the hydration. And here we see for these different water-cement ratios that the higher the water-cement ratio, the more the hydration is going on. So hydration and the extent of hydration, it's not just the question of supply of water, it's also very importantly a question of the amount of space available. And we're going to come back to this point in several lectures because this is really the limiting factor in controlling the kinetics after a few days. So the next slides are now talking about how we prepare samples when we want to do these discrete measurements. And these slides were prepared by my colleagues at EMPA because this course, or most of this course, was presented already in Beijing a couple of years ago. And so I want to acknowledge that these were the people who did these slides. And the first point they make, which is another very general, very important point, is to understand about the shelf life of cement. So many people, when they're starting out on a PhD, they get a batch of cement, they spend a lot of time characterizing it, and after about 1 or 2 years, they think, oh, I should have done that experiment. They go back to the same lot of cement, but the problem is it's not the same lot of cement. Usually you can only rely on a cement being more or less stable for as little as 6 months. And if you live in a hot country with a high relative humidity like Brazil, it may be a lot less than that. So in a hot, humid country, you know, even after 1 month, you're going to see changes. And these changes are due to absorption of water by the cement paste. Here, it's a very exaggerated scale down here. So, you know, this is a much higher scale than we'd have for other measurements by thermogravimetric analysis. But you can see in the age sample that there's already been some ettringite and maybe aluminates forming. And this is the impact on the hydration kinetics. So, you know, this is absolutely dramatic. You see the heat at this peak here is more than halved in an age sample. So it's not negligible. It's really dramatic.
Can I just make a comment?
Yeah.
We have in Brazil, it's common for the industry to put water in the mills.
Yeah.
So we had the experience of buying new cements with degree of hydration of 10%, more than 10% of combined water. Additionally to and the gypsum was anhydrite, not or anhydrite. So it is a problem. Most of our cement in Brazil comes pre-hydrated.
Okay.
And it's really, really difficult to change because for the bag market, it really doesn't matter. Yeah. Well, it matters, but they can feel it.
I mean, so I should say that it's normal to add water during milling because during milling the cement gets very hot, and if it's well controlled, it's okay. So it's not adding water per se that's the problem, it's the control of the process. So here we have some results that were done in a NanoCem project in 2011, which studied very carefully the different phases we have in cement and at what relative humidity they would start to absorb water. So here you see the kind of hierarchy. Something like free lime will absorb water. You know, I mean, you can be in the desert and it will absorb water just about. It will absorb water at less than 10% relative humidity. And this is another problem in terms of building materials because if you're buying lime for various purposes, this age is even worse than cement. Here's gypsum. And here's hemihydrate, and of course, you know, you want them to be right down here because if you're going back to this point about adding water in the mill, you want these phases to stay hydrated. And then we have C3A, generally the illuminate phases will start to react at 50%, and C3S, C2S about the same. So how can you try to compensate that? Well, first and foremost, don't buy your cement in a shop. because you've no idea how long it's been in the shop. We had a very big problem with our physicist colleagues who were working on this very sophisticated technique of NMR. And we had one discussion meeting with them, and they said, well, you know, we don't understand these results. And I said, well, where did you get the cement from? They said, oh, we just went to the shop and bought it. I went, my God, I can't believe you did that. And the second thing, store your binders in small batches under low relative humidity conditions. So you get your sack of cement, and what you should do immediately is separate it into small plastic containers. You can seal each one individually, and then you only need to work with one at a time. Because even if you put it in a large barrel, if you're opening and closing it all the time, you let in moisture. And if you do this properly, this is results from EMPA, which they had a sample which was kept in a sealed bucket at 20 degrees C, 35% RH. It's very nice and dry in Switzerland. And you see that really those changes were not very significant during the 4 years, which is really all you want because that's the length of a PhD project. So really pay attention to your samples. And there's quite a lot more in the book about that. The next thing is about mixing. So you can use a lot of different techniques for mixing. Here are some examples. So this is a standard mortar mixer, and this is quite a sort of low intensity mixing. But you have to be aware that if you have a mortar, then a lot of the mixing action is brought by the aggregates. So the fact you have in a mortar, you have aggregates. The aggregates are moving past each other, and this gives quite a high shearing to the cement paste. So if you now want to go and study a cement paste on its own, it's no good to use the same mixing conditions because this will not be the same thing. You really need to go to a much more high intensity mixer of a type like this or this. And in this slide here, you can see again how dramatically for pastes, how dramatically the mixing speed can affect the hydration reaction. So this is hand mixing. And then this is increasing intensity. And when you get to this speed of about 2,000 RPM, you're back to what you can get in a mortar. So this effect just of mixing can affect the hydration kinetics by more than 2 hours. This is really not negligible. And going back to the calorimeter, some calorimeters have this, what they call in situ mixing. Please don't use that. It's really rubbish. This in situ mixing is not mixing the paste at all. You will have a situation which is even less well mixed than hand mixing. It will be somewhere down here, and you will have completely different kinetics. So many people are worried, oh, we don't very well see the first peak. Well, forget about the first peak because you're never going to be able to measure that properly. Mix your sample outside the calorimeter and put it in the calorimeter afterwards. And something like silica fume is particularly a bad issue, particularly because usually when you receive your silica fume, sometimes it's been already densified for transportation. This is very, very problematic. And this shows you how completely different you can get a cement paste with 10% silica fume. Here, if you mix by hand, you can see it's a complete disaster. It's not consolidating at all. And here they've used a high intensity mixer, so you can see it's much better. This is a proper paste sample now. And then if you look in the microscope, you can see these huge big lumps of silica fume, and these will even give you alkali silica reaction. Because it's a big lump, you're reacting with the silica fume inside there, and then it will produce expansion. So silica fume is particularly a problem, and the best way to do it is to pre-disperse your silica fume with a dispersant, like a superplasticizer, already before you even blend it in the cement paste. So, this is what it says. Densified silica causes a lot of problems. Use an ultrasonic treatment or use a slurry. So now if we want to cast our paste for hydration studies, this is generally what we're doing at EPFL. We're making these little cylinders of paste, And the nice thing about these little cylinders is the diameter of this cylinder is the same size as we need for X-ray diffraction. And when we come to talk about X-ray diffraction, this means instead of having to prepare a separate sample each time, you can just cut a slice off. You always have to remove the end and then cut a fresh slice. But then you can cut a nice slice, you can lightly polish that, and you can look at that surface by X-ray diffraction without having to dry your sample or in any other way prepare it, which is extremely convenient and also good because then you have the best quantification of phases like ettringite, as we'll see in the next lecture. And then what you do after 1 day, you take it out of the original container, you put it in another container which is a little bit bigger, but not very much bigger, and you put some extra water around it. So this is for if you want to do saturated curing and keep your sample supplied with water, you want to supply extra water, but you don't want to put it in a large volume of water, otherwise things will leach out of the paste. Particularly like alkalis will leach out. So in many, many papers, you'll read that people say the samples were put in saturated lime water. Well, that's actually completely useless because it's not really the lime that's leaching out, it's the alkalis that are leaching out. And even in saturated water, within a couple of months, you'll have lost most of your alkalis in your cement paste. And if you're looking at something like reactions with SCMs, like fly ash or slag, this is going to have a huge impact on the reactivity of those materials. So this is really how you want to do it. You want to just have a small supply of water, which will very quickly become of the same composition as the pore solution. And then for most of the techniques, we're going to talk a bit more about this afterwards when we talk about MIP and XRD and everything. We're going to need to stop this hydration. We need to get rid of the water. And the main idea is we want to remove the water so we have a stable microstructure, particularly at early hydration times. You'll have very rapid changes, so you want to stop those changes happening, and the easy way to stop them is to remove the water. So, after a month or so, well, the hydration is so low, so it's just used to remove the free pore solution. And for some techniques, so, if we have long term, if we want to look at XRD or NMR, we don't necessarily want to stop the hydration. Right, now what methods can we use? Well, there's these direct drying methods, so summarized as oven drying or vacuum drying or freeze drying. And here the important parameters are the temperature you use, the pressure, the size of the sample, etc. The big problem with most of these methods is that they remove a lot of water from the gel pores of the CSH and also a lot of water in ettringite and AFM. So none of these techniques are really very good, and particularly, we're going to come back to it, oven drying is a disaster. Unfortunately, this is the most popular method in the literature, but if you put your sample at 105, well, forget about doing any microstructural characterization because it's really total disaster from all points of view. It destroys the hydrates. It changes completely the pore structure. I mean, it's really a disaster. Then we have solvent exchange methods. So there's quite a lot of different ones you can read about. First, we were working with methanol, and then people said, oh, you shouldn't work with methanol because it's got some health issues. So then we switched to isopropanol. We're still using mainly isopropanol. Sometimes we're also using acetone. These are really both very good techniques for removing water. And of course, there are still some issues about how long you do it, and methanol particularly interacts strongly with the hydrates, which is another reason for not using it. And there's a lot of details in the literature, which are given in the references in the chapter. So this just shows you some examples of how you can really affect particularly these aluminate hydrates. So you see, this is what we're generally doing for X-ray diffraction. We're doing slices without any stopping because you can slice, you can put it in the X-ray diffractometer, and you can do the whole measurement within half an hour or so. So you're not going to have very much changes happening in that time. And here you can see the peak for ettringite, in this case for hemicarbonate, monocarbonate, and this is the ferrite reference. And you'll see the ferrite, which is an anhydrous phase, is generally not changing between these different traces. And then we see this method, which was quickly stopped with acetone, and then just quickly dried at 40 degrees C, just for 5 minutes to get rid of the acetone. And you see that's pretty good. That's pretty much the same as this one here. But even that same sample, if you, instead of drying quickly at 40 degrees, you just ground it to a powder and stored it in a desiccator, so it's just under vacuum for 1 day, you see already you've really destroyed your hemicarbonate. It's picked up a little bit of CO2, it's gone a little bit to monocarbonate, and the ettringite is much, much less. And then if you've done vacuum drying, which is what a lot of people do, freeze drying is basically vacuum drying. You see, you completely destroyed all these phases. So these hydrates are very, very sensitive to the drying technique. And that just shows you then the same results in terms of the thermogravimetric analysis now, not in terms of XRD. So here we can see that this is the better condition, where we've just removed the free water gently in a vacuum, not with high via, and then we've more severely dried here. So if this is freeze drying, this is isopropanol, they're both about the same. We've lost a lot of that water that was in the ettringite. And the other problem to be aware of, that if you have organics, like coming from additives like superplasticizers, these can oxidize, and these can give you this extra peak here from the carbonation. So this is another example of the impact of the organics that we've, this is the acetone drying, which is the good condition. This is the vacuum drying. So the acetone drying is better here for preserving the ettringite, but it gives you a problem with the amount of carbonates you determine up here. And this is another example of short drying by solvent exchange. To dry a sample in 15 minutes, you'd have to have either a powdered sample or a very, very thin sample. Generally, you have to use much longer, and then that's freeze drying. You see you're losing that water in the ettringite. So here there's a lot of tables. It's very dense text. As most of you have got the book, I'm not really proposing to go through it. What we're doing mostly now in the laboratory is using solvent exchange. This is generally the best. It preserves the microstructure, so certainly for SEM, it's very good. It's the best for MIP. It's, of course, the one thing where it does say XRD here, but I would not use solvent. I would not use any drying techniques for solvent, for XRD. And here, just to summarize, are some hints for sample preparation. These points here were taken from the earlier part of the chapter I didn't cover in this lecture. This part here is what we've talked about here. We've talked about storage, we've talked about mixing, casting, and curing, and we've talked about stopping hydration. So solvent exchange with short freeze drying. Do not apply harsh procedures such as drying at 105. I cannot emphasize that enough, because still today, I would say a majority of people submitting papers are still drying at 105. Unfortunately, it's a method that's talked about in a lot of standards. So in many, many countries, there's this method that's supposedly meant to be for assessing the total porosity in a material, where you dry at 105 and resaturate, or you saturate and then dry at 105. But this value you get out of this, it's pretty meaningless in terms of real microstructure. It generally correlates quite well with the original water-cement ratio. So it has a kind of value for telling you whether you put a lot of water in your paste or not much water, but it doesn't really tell you what the real porosity is. So this is the conclusions of this first part, that the first prerequisite really is this sample preparation. There's very little you can do if you prepared your sample badly in the first place. And I'll talk a lot more about this on the SEM part, because there, you know, you cannot rescue a sample that's been badly polished, for example, or badly prepared. And please, you know, invest the time in preparing your samples well, storing your cement well. It will save you masses of time afterwards. You have to be aware of errors and accuracy. Check your methods by looking at other methods. Report how you prepared your sample. So, you know, in the worst case scenario where somebody wants to go back at the look at the results, they need to know exactly what you did. And above all, never dry your samples at 105 degrees C.